So let's continue working on these exponential equations where we solve them with logarithms. And in these next three problems, you'll see that the base of our logarithm or these exponential equations here is not 10 or e. So we'll have one extra step in these problems. So let's first rewrite this. We have 20 times 7 to the 3y is equal to 5. And the strategy for the most part is the same. It just has one extra step at the end. We're going to solve it for our exponential term. So we'll divide each side by 20 and we'll simplify that fraction. So 7 to the 3y is 5 over 20, which is really just 1/4. And now we'll rewrite this as our logarithm. So this is equivalent to log base 7 now. And the logarithm is always equal to the exponent. So this is equal to 3y. So that means the 1/4 goes on the inside. And let's solve this for y. So we'll divide everything by 3 or multiply each side by a third. So we have 1/3 log base 7 of 1/4, and that's equal to y. So if we try to do this into the calculator, notice we do not have a log button with a base of 7. Now, some of the better calculators do have a button for this. For instance, if you go to the math button, this is one of the better ones, and scroll all the way down, you can find log base, and hit enter on that, and you can customize your base. So you can put a 7 in there, and then 1/4 is just 0.25, and we'll get an answer, negative 0.712. So minus, let me use a darker color here, minus 0.712. But what do you do if you don't have that button? And for that, we'll need to use the change of base rule. So let's just remember that. The change of base rule is that when you have, let's say, log base a of b, you can change this so that we have a quotient of two logarithms where b is in the top, a is in the bottom, and you can make the base whatever you want. So this is equal to log base, let's call it c of b, divided by log base c of a. So as a more concrete example here, since this is probably fairly abstract, if we had, for instance, log base 2 of 8, and you want to check that this is equal to 3 into your calculator, you can use base 10. So we can do log base 10 of 8 divided by log base 10 of 2. And you'll see these are equivalent to each other when you actually evaluate them. They both will come out to be 3. But we can use whatever base we want. We can even use natural logs here. So natural log of 8 over natural log of 2. Since remember, natural logs are just log base e for both of these. So for our problem, basically we just want to change it to a base where we can actually plug it into this calculator. So let's use base 10 for these. So this, let me make a little bit more room so we have some space. We can work over here. So log base 7 of 1/4. You can use base 10. So we can do log base 10 of the input of your logarithm, the top number. So, and I'm going to use 0.25. The 1/4 is fine. And then you'll divide it by log base 10 of your original base. That will now be the input for this logarithm. And again, you can rewrite it with the common log notation, so we can drop the 10. So this is log of 0.25 divided by log of 7. And you can also use the natural log if you want. We can do natural log of 0.25 over natural log of 7. And let me just prove it to you that it doesn't matter what base we use. So this is log of 0.25. Oops, I used 5. So 0.25 divided by log of 7. And that'll give us our answer, which we already got. And we can also use natural log. So natural log of 0.25 divided by natural log of 7. And you'll see that it's the exact same answer. So the change of base rule is very effective if you do not have one of these special customizing logarithm buttons on one of the newer calculators. So with that in mind, let's move on and try some other problems here. So we have 4 times 5 to the negative 6t equals 2000. So we'll rewrite that. 4 multiplied by 5 to the minus 6t is 2000. And we want to solve it for our exponential term. So let's divide each side by 4. So 5 to the minus 6t. 2000 divided by 4 is just 500. And let's just rewrite this with a logarithm. So for that, we have log base 5, since that's the base of our exponential expression. And the logarithm is equal to the exponent, the minus 6t. And so the 500 just goes on the inside of your logarithm. And to solve for t, we'll just divide each side by negative 6. So t is minus 1/6 times by log base 5 of 500. And this one, we don't actually need to find the decimal answer since this is just multiple choice. But if we did need to, we could use our change of base rule. This is still minus 1/6. And now it'll be multiplied by the quotient. We'll use natural log for this. So ln of the top number divided by ln of the bottom number. But like I mentioned, we don't actually need a decimal answer. We just want this exact answer in the original logarithm. And so it's got to be negative log base 5 of 500, and we're dividing by 6. So it looks like choice letter B here. And let's do one more problem like this. Let me just rewrite it. We have minus 15 times 2 to the negative 0.5x equals negative 90. And we'll start by solving for our exponential term. Let's divide each side by negative 15. So 2 to the minus 0.5x. 15 goes into 96 times. The negatives will cancel. And we can rewrite this with log base 2 now. So we have log base 2 of 6. Whatever the exponential expression is equal to goes on the inside. And the logarithm we know is equal to that exponent. So minus 0.5 times x. And to solve for x, we'll just divide by minus 0.5. So we have log base 2 of 6 divided by minus 0.5. We could have also just multiplied by negative 2. But this is equal to x. And we'll need to change the base here so that we can actually put this into the calculator. So let me finish the problem down here. And we have minus 1 over 0.5 multiplied, and I'll use the common log this time. We have log base 10 of 6 divided by log base 10 of 2. And let's use the calculator. So at the end, I'm just going to divide it by that negative 0.5. So we have log of 6 divided by log of 2. And at the end, like I mentioned, we'll just divide it by negative 0.5, and that should give us our answer, this minus 5.1699. So we'd have to round up, and this 9 would also round up to a 7, so it'd be 0.170. So minus 5.170. Let me rewrite that with a darker color. So minus 5.170 is our answer, rounded to the nearest thousandth. And let's check this. We want to make sure that this is in fact the correct answer. So this one is a little bit harder to check with the notation, but if you put everything into parentheses correctly, it should work. So we can do minus 1 divided by 0.5. We'll open parentheses here and put in our log base 6 divided by log, excuse me, I said base 6, but log base 10 of 6 divided by log base 10 of 2. Close that off. We should get back our same value, and we will store that as our variable x, and now type in the original equation. So minus 15 multiplied by 2 raised to the minus 0.5x power. We'll get out of that exponent. We need to test that this is true, so hit second test. There's the equal sign, and this is equal to negative 90. And if we made a mistake, we'll get a 0. But since we got a 1, we know for sure we did this correctly. So once you get back your 1 here, you can feel very confident that this is in fact the correct answer.